quick survey around the office revealed the fact that everybody knows that the power in their homes is 60-cycle alternating current. Half of the people surveyed knew what that was, and only one person knew why it was there. 15 years ago, I could have told you how alternating current kept our clocks and turntables running on speed, and that many of the motors around the house would only work on AC. But times have changed. Most modern electric appliances either require DC, direct current, or they don't care whether they operate on AC or DC. There's one good reason left why the electric company delivers alternating current to our homes, but it requires a bit of a demonstration. That's the effect of too much current flowing in a wire. One solution to the problem is increase the size of the wire, but there's another solution. The work that's done by electricity is measured in watts. And wattage is determined by multiplying current by voltage. Scientifically speaking, volts times amps equals watts. Now, practically speaking, as far as you and I are concerned, we only care about wattage. Wattage does the work, and we're charged for electricity by the watt hour. The heating effect that burned my little wires over here was caused by the current that was flowing, the amperage. So, I can transmit the same amount of work over a smaller wire by sending relatively high voltage, low amperage electricity. Unfortunately, we can't use this high voltage power in our houses because there's a little quirk of high voltage electricity. It likes to jump right through the air. So we want lower voltage electricity around the house, and the electric company wants high voltage on their towers and poles. The solution to all of this problem is George Westinghouse's invention, the transformer. And the transformer is the key to the great alternating current mystery. When a current flows through a wire, magnetic field results. The reverse is also true. But notice, magnetic field can only cause a current while it's moving. That's one of the laws of the universe, and I can't do anything about it. If I put these two bolts end to end, I get an interesting method of transferring power. The battery is going to cause a magnetic field to move outwards in bolt number 1, and it's going to cut across bolt number 2 and generate a current. Briefly. As soon as the invisible magnetic field grows to its maximum size, it's no longer moving, and the current ceases. When I make the field in bolt number 1 collapse, another blip of current flows. The electromagnetic effects are proportional to the number of turns of wire on the bolts. Here's what's inside a transformer. 2 coils of wire on a common iron core. Now, if the 2 coils of wire have the same number of turns, all we have is an interesting scientific effect. If the 2 coils of wire have a different number of turns, we start to get somewhere. The voltage out will be proportional to the ratio of the turns of wire. In other words, if I put 1 volt into these 10 turns of wire, I get 10 volts over here from the 100 turns of wire. Now, by the law of physics that states there's no free lunch, I gain 10 times the voltage at 1/10 the current. But by the volts times amps equals watts formula, the wattage remains the same at both ends.
Hogwash!
Well, the wattage remains almost the same. Some of the electricity goes into heating up the transformer. As a matter of fact, this little model would be so inefficient it would probably melt instantly. A real transformer will have thousands of turns of wire. This was a real transformer. It has a 150 to 1 turns ratio approximately. About 100 volts in gives 15,000 out. Transformers are the reason that all of the electricity in our homes alternates 60 times a second. This is a little more natural than it sounds, actually, because all of our electricity comes from rotary, steam, or water-driven generators. And as the rotor turns with the magnets on it, the most natural thing in the world to generate is alternating current. Now, my oscilloscope shows a pretty choppy version of AC. Real generators have more than 2 wire-wrapped bolts and more than 4 flaky little magnets. Here's some real AC. This is what comes out of the plug in the wall. Why 60 cycles a second? I don't know. The frequency has to be high enough so that the lights won't flicker visibly, and low enough to not be too annoying as electrical things hum away. But if anybody knows where the number 60 came from, they're just not talking. The voltage at the wall plug is supposed to be a nominal 120 volts, but a careful measurement on the oscilloscope screen shows that the voltage actually peaks up at around 170 volts. Because alternating current is constantly reversing directions, it spends some of its time not doing much work. The effect of AC in a heating element or incandescent light bulb is only 0.707 of its real peak value. So, just to be nice, they're giving us 170 volts, but they're calling it 120 volts, just to be fair. Incidentally, I know where the figure 0.707 comes from, only I'm not talking. Heating elements heat because of the current flowing in them. They don't care which way the current's flowing, so they can use alternating current directly. An incandescent bulb can just be considered to be a special case of a heating element. The filament, heats up to the point where it gives off light. Here's an interesting trick with AC, though. A 10-cent component called a diode will let current flow only in one direction. And by inserting a diode in the circuit, the wrong way half cycles are blocked and the bulb runs at half brightness. Simple dimmers that have a full and half position use the 10-cent diode. They don't charge you 10 cents for it either. Huh. Now, a lot of things require a steady source of current, direct current, the kind that comes from batteries. Putting the diode in the circuit gets us halfway there. Current's no longer going backwards and forwards, but it's still going on and off. The tape player running on this kind of power sounds like this. To finish conditioning the current requires a capacitor, or condenser if you're over 50 years old. The capacitor is a little like a rechargeable battery with a very short life. When the AC cycle is at its peak, it charges up, and then it powers the device while the AC is busy dipping to nothing. Now, if the capacity is too low, the effect isn't perfect, and you'll still hear some humming. Now that I've just told you what's wrong with your tape player, there's one more thing to know about it. My little demonstration with one diode actually throws away half the cycles. There is an arrangement of 4 diodes that's used in most power supplies that folds those unused half cycles in the correct direction. When a power supply like that starts to hum, the hum is double at 120 cycles per second, because that's twice 60 cycles. But I still don't know where the 60 comes from.